So, today we're going to talk about something really big, a fundamental shift in how we actually build computers. See, we're moving beyond the simple goal of just making things faster and faster. We're entering a whole new era of computing, one that's inspired by the most incredible processor we know of, the human brain. Let's dive into how we're building computers that can genuinely think.
Okay, so this right here, this lays out the entire challenge perfectly. On one side, you have our most powerful, most advanced AI systems. And these things can guzzle hundreds of watts of power. It's an incredible amount of energy. But then on the other side, you've got the human brain. It's performing absolute miracles of learning, creativity, and perception, all on about 20 watts. That's just enough to power a dim light bulb. This massive, staggering gap in efficiency, that's the problem we have to solve.
You know, for the longest time, the solution in computing was pretty straightforward. Just throw more power at the problem. More transistors, faster clocks. But that brute force approach, well, it's hitting a wall, a hard wall. Physically and economically, we've pretty much reached a dead end with that strategy.
So if we can't just keep building bigger and bigger hammers, what do? Well, the answer is to build smarter ones. It's time to stop overpowering problems and instead start thinking like a brain. And that brings us right here to neuromorphic computing. Now, the distinction here is absolutely crucial. So let's be clear. This is not about running a simulation of a brain on a regular computer. No, this is about building the brain's core architectural principles, its very structure and way of working, directly into the silicon itself.
So, how does this actually work? Well, the first core principle is something called spiking neural networks. Instead of the constant, power-hungry stream of ones and zeros that our current computers use, these chips communicate only when it's necessary. They use these short, efficient bursts of energy called spikes, which is exactly how neurons in your brain talk to each other. It's kind of a speak only when you have something important to say approach, and it's the very first step toward achieving that massive efficiency.
And that spiking behavior, it makes the second principle possible, which is really the secret sauce to its efficiency: event-driven execution. Okay, think of it like this: a motion-activated light versus a light that's just always on. This chip only wakes up and uses power when an event, a spike, actually arrives. If there's no new information coming in, it just sits there, silent, using almost no energy at all.
And this really gets to the heart of the whole idea. Right now, on your laptop or your phone, even when it's idle, it's still costing energy. There's always something happening. But in a neuromorphic system, silence costs nothing. If there's no data to process, there's absolutely no power being spent.
The third big idea is asynchronous processing. So, think about any traditional chip. It has a central clock, this constant, rigid heartbeat that forces every single part of the chip to work in perfect lockstep. Neuromorphic chips, they just get rid of the clock entirely. Different parts of the chip can work totally independently, firing up only when they're needed. It's a simple idea, but it saves an absolutely massive amount of energy.
All right, so we've got the concepts down. Let's see how these principles are actually being turned into real hardware. This isn't just theory anymore. We're talking about building hardware that has its own nervous system.
And this stuff is happening right now, in the real world. You've got major players deep in this game. Intel has its Loihi research chip. IBM developed its TrueNorth chip. These aren't just science fiction projects. They're actual, tangible examples of silicon that has been designed from the ground up to operate just like a brain.
Now, a really key piece of this whole puzzle is a tiny component called a memristor. You can basically think of it as an artificial synapse. And its superpower is that it can both process information and remember it in the exact same physical spot. Now, this is a total game changer. It means learning can happen directly on the chip, which gets rid of that huge energy-wasting bottleneck of constantly shuffling data back and forth between a processor and a separate memory chip.
But it's really important to get this straight. We're talking about a brand new kind of tool here, not a replacement for everything we already have. Which, of course, leads to the big question, right? Does this mean it's the end of the line for the trusty CPUs and GPUs that we've relied on for decades? Are they on their way out?
Well, the short answer is no, not at all. It's really about using the right tool for the right job. See, neuromorphic computing is set to completely revolutionize specific areas where our traditional hardware just struggles. Think about AI running on small, battery-powered devices out at the edge, or autonomous robots that need to see and react to the world in real time, or really any system that needs to be intelligent without being plugged into a wall. That's where this technology is going to absolutely shine.
So as we start to wrap this up, let's just zoom out and look at the really big picture, because this is so much more than just a new piece of hardware. It's a fundamental shift in the entire paradigm of computing. We're moving away from the singular focus on just being faster, and we're moving toward creating systems that feel, well, alive.
And that's the ultimate goal here. Not just artificial intelligence, but complete artificial nervous systems. We're talking about systems that are adaptive, that are perceptive, and incredibly efficient. Systems that can learn and interact with the world around them in a way that feels truly intuitive.
You have to realize what a massive change in philosophy this is. For the last 70 years, the name of the game in computing has been speed. How fast can we go? But that's just not enough anymore. Faster isn't the goal anymore.
Alive is. And that one simple idea, well, it's poised to define the next century of technology.